and welcome to our course, Giving Shapes to Blobs, an introduction to point set topology. This is week 1, part 1. Before we get started, a quick introduction. Our names are Angela
and Todd,
and we both study mathematics. I study geometry at the London School of Number Theory and Geometry.
And I study the mathematical theory of computer science at UCL.
Topology plays an important role in both of our work, so we decided to teach this as a topic. So let's get started. The first thing to note is that our course is called Giving Shapes to Blobs. So an important question to answer is, what is a blob? Now for us, when we say blob, we just mean any object to which we want to give shape. And in math, these objects are known as sets. So we'll be using the word blob and the word set somewhat interchangeably during the rest of this course. But not to worry about these sort of weird words, let's just take a look at some examples of blobs, and I think you'll quickly catch on to what sort of objects we're talking about. So for example, I might be interested in studying a collection of points. So if I have 3 points, that could be a blob. Alternatively, maybe I'm interested in studying a set of numbers. So maybe I'm interested in 1, 2, 45, 678, and negative 12. This collection of 5 numbers forms a blob. Right here, in this lower quadrant of the screen, I've drawn another blob. It's one of my favorites. It's called the empty blob, and it contains absolutely nothing. Sometimes we denote it as a circle with a slash through it, and that's just what we call the empty blob or the empty set. Maybe we're interested in something a bit more interesting, so a blob that consists of all of the points inside of a square. And so you can pretend that this entire square is shaded in, and this would be an infinite collection of points which form a blob. So that image that we saw at the beginning, well, that's a blob too. It could be the blob containing a set of eyeglasses and a weird green shape, or it could be maybe all of the points that are contained inside of this drawing. In any case, it's a blob. Now let's talk a little bit about blob notation. So whenever we have a blob, we can use curly braces to denote it. So for example, the blob 1, 2, 3 dog hat Angela is just the blob consisting of the elements 1, 2, 3, a dog, a hat, and me. Blobs can contain, as we saw, finitely many things. So for example, this set right here contains 6 objects, or it could contain infinitely many things. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is a blob consisting of all of the whole numbers. But note that in this case, the curly braces are a bit misleading. So when I look at the set 1, 2, 3, and so on, is that all of the whole numbers, or is that just 1, 2, 3 dog hat Angela again? So whenever we're talking about infinite sets, we're going to be able to describe them using other words or other notation, so you won't have to worry about ambiguity with the curly braces too much. And now we can talk about how we perform operations on blobs, or how blobs are related to other blobs. So first off, we have something known as intersection. So the intersection of 2 blobs, A and B, is a new blob C consisting of all things that are contained in both A and B. So for example, if I have this blob A, which just consists of all of the points inside of this weird bean, and I have this blob B, which just consists of all the points inside of this, also a weird bean, then their intersection is going to be all of the points that they share, that are contained in both A and B. So for us, it's going to be this area here. This is going to be our blob C, and we often denote this with a little bump like this. So this is A intersects B, and that's C. Okay, Okay, so the next thing is something called the union. So the union of two blobs, A and B, is a new blob C consisting of all the things contained in both A or B. So this is a little bit different from intersection. So if again I have A and I have B, the union is anything that's in A or B. So yes, we include this sliver, but as long as you're in one of A or B, you get included. So C consists of this super big set that contains everything in A and everything in B. So this is C, and we denote this A union B with a little U. And note that this is sort of the opposite of intersection in some sense, both in the symbol and in what we mean. Okay, so the next thing is something called a subblob. So, or subset. So whenever all of the elements of A are contained in B, we call A subblob or a subset of B. So for example, if I have a nice big blob B and I have A, which is, I don't know, maybe this bean and 3 other random points, this or 4 other random points, we call this thing A, then A, all of the points in A are strictly contained inside of the points in B. So A is a subset of B, and we denote this with a sort of sideways U, always with the open end towards the bigger set. And note that A could be contained in B is a pretty generous thing. So for example, A could consist of all of the points in B, and A would still be a subset of B. So subblob is sort of useful, and we'll see why soon, but it's a very generous sort of idea. Okay, finally, we have the following situation. So let's say we have a big blob C with subblobs A and B. So when the elements of a subblob A are all of the elements not in B, then A is the complement of B. So let's see this in action. Let's say we have this bean here. This is B. Then A is going to be anything not contained in B. So A is going to be all of C except for B. Let's say this is A. And in this case, A is the complement of B. And likewise, B is the complement of A. All right. All right, finally, let's talk about giving shapes to blobs. So the shape of the blob for us is going to be given by something called the topology. The topology is going to tell you which of the subblobs of a blob are open. So open is a very special quality. When a subblob is open, its elements will have some notion of sticking together. And we'll see more what this means later, but for now, let's get to know the definition of topology. So here's the definition of topology. Let B be a blob. The collection of open subblobs T of B is going to satisfy all of the 3 following axioms. Firstly, the empty set is in T, and so is B. So the empty set is going to be an open set, and so is the entirety of B. Secondly, if C and D are in B, then so is C intersect D. So what this means is if I have a set C, which is open, and another set D, which is open, then their intersection is also considered open. Likewise, thirdly, if C and D are in B, then so is C union D. So if C is open and D is open, their union, this set here, is also considered open. So any collection that satisfies these three things is called a topology of B. Topology just means a collection of open sets satisfying these three rules. You'll see these three rules come up over and over again for the rest of the course. Okay, a little bit more about topology. Sets in the topology, as we said, were called open, and open sets in a blob are special because they have some quality of sticking togetherness, which we'll see more of later. Now, if a set is the complement of an open set, it's going to be closed. Mathematicians are very creative when it comes to naming things sometimes. And now, this is the weird thing, sometimes sets are both open and closed. And when this happens, we call them clopen because we are serious and dignified mathematicians. All right, now let's take a look at some examples of topologies. So here is our favorite set, 1, 2, 3, dog, hat, Angela. And we're going to try to build a topology on this set. So let's recall the definition of topology, right? The first axiom says that we need to include the empty set and the entire set. So what I'm going to do is I'm going to circle, if I circle a collection of points, that means that they form an open set together. So over here, I'm just going to write the empty set over here so that we remember that this empty set is one of the sets in our topology. Obviously, I can't circle the empty set. That doesn't really make much sense. But also, I can circle all of the points, and that would be an open set. Now, do I have a topology? Well, what are the other two axioms of topology? Right? It has to be closed under intersections, meaning if I take any two sets in the topology, their intersection will be in the topology. So what's the intersection of the entire set with the empty set? Well, that's just going to be the empty set. And likewise, the empty set intersected with the empty set is also the empty set. And this entire set intersected with itself is, again, its entire set. So we satisfy closedness under intersection. So what's the third axiom of topology? It's closed under unions. Okay, let's check if this satisfies that one. What is the union of the entirety of the set with the empty set? Well, that's just the entirety of the set again. And what's the union of the entirety of the set with the entirety of the set? That's the entirety of the set. And what's the union of the empty set and the empty set? Well, that's the empty set. So in fact, this topology, which consists of only two sets, is a topology. And in fact, it has a special name. It's called the trivial topology because it's kind of silly. And this topology is interesting for the following reason. If somebody gives you any blob whatsoever and asks you for topology on it, you can always give them the trivial topology and it will always work. So I guess it's nice for that one reason. Okay, let's take a look at another topology maybe. Something maybe with a few more open sets. So as usual, we need to include the empty set and we need to include everything. Now let's say that we really like hats, so we want hats to definitely be an open set, and we really like 3, the number 3, so we want 3 to be an open set, and we definitely really like dogs because what kind of psycho doesn't like dogs? And so now we've declared that 3, dog, and hat are definitely open sets on their own. What else has to be an open set? Well, remember, we need to satisfy the 3 axioms. So we need to make sure all of the open sets are closed under intersection and closed under union. So what that means is that intersections of these 3 things have to be open sets. I think we're good though, because none of these 3 sets intersect each other. We also need unions. So what's the union and 3 and dog? Well, that's just going to be, maybe I'll use a different color because things are going to get messy. Well, that's just 3 and dog. That's going to be open. Dog and hat, likewise, will have to be an open set. And 3 and hat has to be an open set. Okay, but there's one more, right? I can take the union of 3 and hat. That's going to be the set 3 hat. And I can take that union, the set dog. So the set 3 dog hat, or 3 hat dog, or hat dog 3, it doesn't really matter the order, I suppose. This also is an open set. All right, can I get any more open sets by taking unions? I don't think so, right? If I take the union of anything within these 3, it's always going to be contained within these 3. And then I could take the union with the empty set, which doesn't add anything. Or I could take the union with the whole set, like with the whole blob, and that would just give me the whole blob. So what I've circled here is another topology. You'll note that I have 3 elements here that are sort of just floating in the nether, and they don't have an open set structure around them. And we'll see what this means in a later lesson. But let's take a look at one final topology. So let's say I don't like that floating in the nether feeling of those 3 elements, and I want to declare a topology where every single one of these elements is contained in its own open set. As usual, I need to remember to include the empty set and the set containing everything. And now let's take unions. All right, well, pairwise, I'm going to be able to pair 1 with 2, 1 with 3, 1 with dog, 1 with hat, 1 with Angela. That's just 1. With 2, I can take 2 and 3, 2 and dog, 2 and Angela, 2 and hat. Okay, and then I need to do 3 and dog, 3 and Angela, 3 and hat. I think this is getting a bit messy. Angela and dog, dog and hat, hat and Angela. Okay, that's all the pairwise ones. Now I need to take sets of 3. So I guess I could start with 1, 2, 3, and then I could take 1, 2 dog, and then 1, 2 hat, and then 1, 2 and Angela, not dog yet. Okay, but well, maybe I'll just include this one for now because 1, 2 dog, hat, Angela is definitely going to be a union. And then I have to take 1, 2, 3 dog and dog, hat, Angela, and I think I've gotten myself a little bit lost, but I think you get the idea of what's going on here. Every possible subset is going to be open in this topology. This is a very special topology. It's called the discrete topology. And just like the trivial topology, the one that was the simplest possible topology, the discrete topology is going to be available for the taking on any blob. It's always going to be a topology. But in a way, it's as meaningless as the trivial one. Instead of having the fewest possible open sets, the discrete topology says, I give up, everything is an open set. So we're going to see more about this later as well. So this is a good example to keep in mind. All right, so I've shown you several examples of topologies. Now it's your turn. Take a look at the first set of exercises. You'll be working on the different operations on sets and on the idea of the topology. And once you've had a good go at the exercises, come back for lesson for the second part of this week 1 class.